So good afternoon all. Are you guys having something or like why is the turnout so low this time around?
So we joined the link using the link given on Moodle.
All this while we were using this link. You guys forgot about it. Remember?
Sure.
From starting we were using this link because of the recording problem. Anyways,
Yes,
I mean,
sir.
yeah, that's
So I
fine
think
actually.
students are dealing.
Okay, that's fine actually. I've alerted them on Viber. Anyways, so this session is definitely going to be recorded, so there is no problem with this. This is the last tutorial that we will be having, right? Next week, we won't be having any tutorial. And this week, whatever tutorial we had, whatever tutorial we have, it's a pretty simple tutorial. So all of you have submitted the tutorials. Have you guys managed to submit the tutorials?
Yes,
Yes, sir.
Okay, then what I assume is definitely when I'm just going, when I'll be just going through the solution, most of you will already be knowing this, right? It is just directly feeding into the formula and getting the solutions, isn't it? Right. So let's quickly go over them. Right. There's only two problems. So question number one, it is to design a class B output stage with the VCC equal to VEE. We need to drive a load resistance of 30 ohms. Each transistor may dissipate on average not more than 0.5 watts power, right? Assume that the amplifier is driven by pure sine wave input whose peak amplitude is there any peak amplitude given away? Okay, peak amplitude is V naught, right? V out, right? That is actually shifted over here. So ignore that. Neglect the saturation voltage of the transistor. A, what is the largest value of VCC? What is the largest value of VCC we can use so that we will not overheat the transistor? So how do we go about doing this? We know the power, isn't it? We know the power that needs to be dissipated by each of the transistor. So what else do we know? We know the load resistance, and we need to calculate VCC. So we can use the average power delivered by the transistor, right? Let's just go through the formula. Okay. Since we are talking about 0.5 volts delivered by each transistor, right? Each transistor. So what happens is the average power delivery formula is this, right? 2 times VCC squared divided by pi squared RL. Now it is what we know is we know the average power delivered by one transistor. So that would be half the maximum power delivered, isn't it? So in this particular case, what we'll be using is this particular formula, right? 2 times VCC squared upon pi squared RL, right? Multiplied by half, because each transistor is going to contribute half of the power, isn't it? So it will be multiplied by half. So from this, we know the average power delivered, that is 0.5 watts. We also know the load resistance, that is 30 ohms, right? So we know RL, we know PD, right? The power delivered, and we need to calculate VCC. So solving this particular formula, solving for VCC, using these particular variables, we will be getting VCC equivalent to 12.16. Are you guys getting that? Did you guys get that? Okay. Next is, okay, great. So next, moving on to part B. For the values of VCC determined in, for the value of VCC determined in A, right? Whatever value we found in A, what value of output voltage, right? What value of output voltage will result in the maximum heating of the device? So we need to find the V out at which it will have a maximum heating. So the maximum VCC, we have already found the maximum VCC, right? So using this particular formula, right, we know that V out maximum is basically equivalent to 2 VCC divided by pi. So we have already calculated the maximum VCC in part A, that is 12.16. So taking this particular value, substituting into this particular formula to get V out max will give us 7.74 volt. Okay. This is directly from the formula, right? This formula can also be found in your lecture slide as well, right? It is V out is basically equivalent to 2 VCC divided by pi. Okay. Yep. So next is part C. If we use VCC of 9 volt, what peak current must the supply be capable of the volume? I mean, what peak current must be the supply be capable of if the volume is turned all the way up, right? If you use 9 volt, right, VCC is equivalent to 9 volt. We need to find the peak current at the maximum value, at the maximum volume. So what we can do is we can, I mean, basically it has said that we have to ignore the saturation voltage. So in that particular case, I peak, right? I peak is basically equivalent to VCC divided by RL. If we had to consider the saturation voltage, it would have become VCC minus the saturation voltage divided by RL. However, it said in the question, it did say neglect the saturation voltage of the transistor. So it will be just VCC divided by load resistance. So we know that the VCC value that we are supposed to use is 9 volt and the load resistance is 30 ohms. So VCC divided by RL is going to give us the peak output current, right? That is equivalent to 300, approximately 300 milliamps, right? So to be exact, it will be around, yeah, it is 300 milliamps, right? Yeah. So that's part C. And then part D, if we apply sine wave with peak amplitude of 4 volts, then how much power is delivered to the load? So in this particular case, we have to find the load power that is basically given by, right? The load power of one transistor will be, yeah. I mean, not one transistor, actually. The load power is basically given by half V out peak squared divided by RL, right? Basically, when we are calculating our the AC power, it is basically V out divided by √2, right? That is the RMS value that we should be using. So in that particular case, V out divided by √2 squared will be just half into V out squared divided by RL, right? So I believe you are able to find this, right? You can also get this. I think it's here somewhere. It is somewhere in your lecture slide as well, right? Yeah, right. Load power is basically given by half V out squared divided by RL, right? So using that particular formula, we know that the peak output voltage is 4 volt, right? So 4 volts squared, right? So half 4 volts squared upon 30 is going to give us 0.267 watts. So the power delivered to the load at this particular peak amplitude is going to be equivalent to 0.267 watts. So anyone has any queries regarding question number 1? Basically, the formulas were there. You just need to plug in the values, okay? So everyone is okay with question number 1? Okay. Let's move on to question number 2. Let class A amplifier with bias current 500 milliamps, right? So there is a class A amplifier which has a bias current of 500 milliamps. Use power supply positive and negative 5 volt, and the saturation voltage of the input transistor is 500 millivolts. Sorry. We plan to drive the amplifier with a sine wave input whose peak amplitude is, it's basically denoted by V out peak, right? By this particular symbol over here. What is the smallest load resistance that we can drive if the maximal symmetric swing is to be achieved? So basically we have to find the smallest load resistance. So from this, we know that the VCC value is 5 volt, right? We also know that the saturation voltage is 500 millivolt. So we need to find our load resistance. We also know the bias current is 500 milliamps. So load resistance in that particular case would be given by, load resistance is basically given by VCC minus VCE saturation. Remember, if the VCE saturation is given, so it will be VCE saturation. So we have to subtract it from the VCC value, right? So VCC minus VCE saturation divided by the bias current, that is IQ, right? That is going to be equivalent to VCC value that is given as 5 volt, right? Remember from the question, the VCC value is given as 5 volt minus the saturation voltage, right? This will be the voltage drop from the collector to the emitter, right? Minus 0.5, right? So we know the voltage that is going to go to the load, that is 5 minus 0.5. And then the bias current is going to be the current across the load, right? So that is 5 minus 0.5 volt divided by 500 milliamps. That is going to give us the load resistance, right? So our load resistance will be equivalent to 9 ohms. Is that fine? Okay. So it's pretty simple, eh? All this one, I mean, all the questions are pretty simple. You just need to plug in the values, right? B, what is the highest possible power efficiency? So when we talk about power efficiency, so it is power output divided by power input, isn't it? So in this particular case, the power output will be basically the output voltage divided by the load. I mean, it will be basically given by half times V out squared, right? It is the power output is basically half into voltage output, that is VCC minus VCE saturation squared divided by RL, right? It is the same formula that we have used over here. It is the same formula for power output, that is half into VCC minus VCE saturation. This part VCC minus VCE saturation is our output voltage, right? That square divided by RL upon, right? The input power is basically from the two from the emitter and the collector. So what happens is, since we are supplying both power to the collector and the emitter, right? So there's two transistors in a class A amplifier, right? So what happens is it is going to contribute, both the emitter and the collector will be, I mean, both the transistors will be contributing power. So in that particular case, it becomes 2 times VCC times bias current, right? So VCC times IQ is going to give us the power, but there's two transistors, right? So they both will be contributing power. So it will becomes 2 VCC times IQ, right? So this is the efficiency formula. So what we know is, we know the VCC value, we know the VCE value. We also know the load resistance that we have calculated in part A. And we also know the bias current. So directly substituting all the values, right? Substituting RL value, right? That is 9. The VCC value, that is 5. And the VCE value, that is 0.5. So VCC minus VCE is going to give us 4.5 squared. And our VCC value is again 5 volt, and our bias current is 0.5 or 500 milliamps, right? So using the standard units, that will be 0.5 amps. So calculating the efficiency, it will come down to 22.5%. So did you guys get that? Great. So you guys are smart, huh? Honestly, you guys are smart. Seems like, the tutorial submissions are actually working. You guys are doing your research, I mean, like doing your studies on your own, right? So that's a good thing, actually. C, in order to achieve the efficiency predicted in B, right? Whatever efficiency we got in B, what should be the V out that should be used, right? So remember, like I told you, right? Directly taking this power output, right? This part, the numerator of the efficiency formula, if you directly take this and compare it with this average power delivered to the load, you can see that this particular term, VCC minus VCE, is our V out, right? V out is basically VCC minus VCE, right? So V out is basically equivalent to, even if you see a transistor, it will be VCC minus the drop across the collector emitter, right? That is the VCE saturation. And whatever voltage is left is going to be passed on to the load. So it is, V out is basically equivalent to VCC minus VCE saturation. That is basically equivalent to 5 minus 0.5, right? 5 volt. This is VCC is 5 volt and VCE saturation is 0.5 volt. So 5 minus 0.5 is going to give us 4.5 volt, right? Next is D. If we use the amplifier at the full volume, how much energy will be consumed in 1 hour? So that means whatever power, if we are using at full volume, what that means is basically whatever input we are supplying, whatever input power we are giving, that is going to be our output, isn't it? So that will be the maximum energy, right? So energy is basically equivalent to the maximum power delivered, right? When you are moving the speaker volume to its maximum, so that means maximum power, right? So energy is basically equivalent to maximum power multiplied by time. So how do you calculate maximum power? Maximum power is going to be basically 2 times VCC times bias current, isn't it? This is going to be our maximum power, right? That could be delivered to the load. So in that particular case, maximum power delivered is going to be 2 times VCC times IQ, right? Or the bias current, right? So in that particular case, VCC value is 5 and our bias current is 0.5 amps, right? Taking these values and substituting over here. And what else do we know? We are talking about 1 hour. So in 1 hour, how many seconds do we have? Remember, when we are trying to calculate power, energy, all this stuff, we always try to use the standard units, isn't it? So the standard unit of time is seconds. So we are talking about 1 hour. So 1 hour converted into seconds is going to be 3,600 seconds. So power times time is going to give us energy. So in this particular case, the maximum power is basically given by 2 times VCC times IQ. So that is 2 times 5 times 0.5. That is going to be just 5, right? 0.5 times 2 is 1 times 5 is 5. So 5 times 3,600 seconds is going to give us 18 kilojoules, right? So all of you got that? Okay. So that's great. So anyone has any queries regarding this week's tutorial or anything like that? You can turn on your mics if you have to. Okay, so I assume everyone is clear what needs to be done. Anyone has any queries apart from this week's tutorial? Anything that you need to know apart from this week's tutorial?
So is Lab 8 assessed because we do not see a portal on Moodle, sir?
I'm not sure because that is supposed to be, I mean, like your lecturer hasn't said anything to me. I'll ask him and I'll let you guys know, because what I was aware of, like all the labs, if we are conducting all the labs, and all the labs will be assessed, right? So that needs to come through your course coordinator, whether we are going to assess this or not, right? So
Yes,
I'll
sir.
let you guys know, right? I'll let you guys know. Or what you can do is also you can
Okay.
drop in query in the group. You can tag Dr. Mehta in it, and he'll respond in that case, right? Or otherwise, I'll ask him again. Okay. Anything else apart from that? So when is your short test? Next week or this week? It is next week, yeah?
Next week, Tuesday, sir.
Okay. So all the best for that, right? And this is probably the last class I'll be having with you guys, because next week we won't be having any labs, no tutorials. So this is the last class that I'll be having with you guys. So yeah. So if you guys have any queries, you can always drop me an email, or definitely the Viva group is there, or you can directly message me, right? If you have anything important that is related to you. Otherwise, all the best with your exams, all the best with your short test as well as your final exam, right? And most probably I'll see you next year if I'm around. If not, then All the best for your remaining years at USP. Okay. So bye for now.